So in this video, we're going to consider the all pairs shortest path problem. So unlike the previous problems, instead of computing the distance of v from S for everything, we're going to compute the distance between any pair u and v for every pair. So we're making a distance matrix between all pairs instead of just a list in the previous example. So in the previous example, for here we have, say, different vertices. We have like u, v, w, u, v, w. And in the middle, we have the distance from u to u, which is going to be 0. These are 0. Then you have this is the distance between u and v. And it's symmetric because we're looking at undirected graphs. But if it was directed, they would just not be symmetric, but can still do the same thing. So you're computing this huge matrix of distances, whereas in the last problems, what we computed was basically a single row. So we fixed the start vertex, which we called S, and we just wanted a list of d of SV for every possible endpoint v. So now we're just generalizing this to allow both the start and end to be a variable. Now, the easiest thing we could do to solve this problem is just using single source shortest paths for every start node S. And you could do this, but it generally won't be as efficient. So here we're going to consider one way to solve this problem using a combination of divide and conquer and dynamic programming. So in particular, we're going to do something very similar to this recurrence, but instead of looking at the last edge each time, so we're always looking at the last edge and recursing to the previous predecessors, this time we're going to try a divide and conquer approach. So the key insight is any path from u to v has a middle vertex. So before we used the fact that any path from u to v has a last edge, and now we're going to use this different characterization. So in particular, if you had a path u to v, it has some intermediate node w, and then continues on to v. Now this isn't true if the smallest path from u to v has only a single edge, but that'll be our base case. So what do we want to define? We're going to define this function dist of u, v, l, and this is going to be the length or total weight of the shortest path from u to v that has total length or total number of edges at most L. So this is essentially the same thing as before, the distance I function. L is taking the role of I here. But the difference now is how we're going to compute this. So recursively, we'll do the following. The main thing we want to do is we're going to take a min over all possible middle vertices, I'll call it W, of the distance from u to w, which takes at most L over 2 steps, plus the distance from w to v, which takes L over 2 steps. So you might be wondering, why is this an L over 2 instead of like L minus 1, which is what we did in the past. We had an I minus 1. So the reason is because we're assuming this is the middle vertex. So in particular, if it's in the middle, the number of edges here are at most half, and the number of edges here are at most half, if the total thing has length L. So you can also call this algorithm middle first search, because the idea is you're first finding the middle vertex, and then recursively, you're going to compute the shortest paths in each block. So clearly, the shortest path from U to V, if it has larger size than one edge, is going to have a middle vertex. Then you need to recursively find the optimal paths from U to W and from W to V. And naturally, we're going to try all possible W because we don't know in advance what the shortest path is, and so what W defines the shortest path, the middle node on the shortest path. Okay, so this is the main recursive part. We're just going to try all possible W, and when I say all possible here, I mean all possible in V. So before, we only looped over things adjacent or that go into V, which isn't the whole list of vertices, it's just a couple of them. The downside here is we now have to loop over every possible W because we don't know in advance whether any vertex could be in the middle. We don't really know. So we have to try them all. So what's the base cases? Well, of course, if L equals 1, then we just get the weight from U to V, because that's the only path from U to V that has size, that only uses one edge. And we can also have separate base cases for if such a thing doesn't exist. So to be precise, it might be the case that there is no U to V edge. So if L equals 1 and no U to V edge, then the answer is infinity. There is no way to get from U to V in one step, in other words. Okay. We can similarly define a special case for when U equals V to set it to 0, but we won't bother with that in the recursive part. That's something we can do with initialization outside of the main recurrence. All right, so now that we have our recurrence, we need to figure out the dependencies in evaluation order. Well, obviously we have dependencies on smaller values of L. We have dependencies on all possible W, so the order there doesn't really matter. So ultimately, what would a good evaluation order be? Well, we can evaluate this in particular. Note that for the first case, we need to compute all the ingoing things to W first. Whereas in the second case, we need to compute all the outgoing things. So it depends on which case we're looking at.